What is FZI? It's defined as a flow zone indicators. The FZI is a technique to identify hydraulic flow units within the reservoir by the integration of petrophysical parameters, mainly core porosity and core permeability. It also provides insights about pore geometry in complex reservoirs such as carbonate. It also improves reservoir description and understanding in terms of pore geometry variation within different lithologies. This technique can be applied through the equation FZI, which is a flow zone indicator, equal reservoir quality index RQI divided by normalized porosity index. For more illustration, let's see an example in carbonate rocks. These sections photos have been taken from different rock samples for the same carbonate reservoirs. Look how different is the pore size and geometry from sample to another from the same reservoir. So hydraulic flow units or zones existence is linked to variation in pore geometry in reservoir rocks. This variation is mainly attributed to depositional nature and most importantly diagenetic controls, which yield distinct zones with similar fluid flow characteristics. So understanding the complex variation in pore geometry within different rock units is important to understand reservoir quality and to exploit reservoirs economically. Why do we need FZI for reservoir characterization and modeling? First, it adds to classify the reservoir units into rock types based on petrophysical properties, variation and dynamic characteristics. It also can be used to evaluate reservoir quality based on porosity permeability relationship. It's also very powerful in heterogeneous reservoirs such as carbonate reservoirs, fractured reservoirs. It's also applicable in clastic reservoirs and shaly sandstone reservoirs. It characterizes similar production properties units, and when incorporated with other geological attributes such as rock texture and mineralogy or autogenic minerals, we will be able to divide reservoir into zones. The essential classical discrimination of rock units with similar petrophysical properties is based on the empirical relationship between porosity and permeability log. Sometimes this relationship doesn't reflect a significant regression. Instead, data could be scattered like in this example, which shows that permeability is varying by several orders of magnitude for porosity unit, which indicates the existence of layers in the reservoir with different pore geometries, hence different production behavior. So, since the relation between permeability log and porosity is proportional, whereas log K is linearly proportional to porosity, we use this plot to predict permeability in general. However, the slope, intercept and degree of scatter of points as well as trend vary from reservoir to another. In general, this variation is attributed to different texture, diagenetic history and compaction degree for both sandstone and carbonate reservoirs. So when the plot shows scattered patterns as we see here, it signifies that there is no possible correlation between porosity and permeability. So it can be noted that per porosity unit there is a significant increase in permeability by several orders of magnitude. However, in sandstone this could be attributed to variation in grain size, whilst in carbonate it could be related to presence of microfractures within skeletal grains or fractures in the reservoir or variation in grain size of the skeletal limestone. So, to define good correlation, we use FZI technique to create clusters that reflect a proper correlation, which we then can use to predict permeability per rock unit relative to porosity. So what are the factors that negatively impact FZI? First one is clay minerals, as they are considered the pore blockers, such as kaolinite, which is the pore filling mineral, chlorite as pore lining, and illite as a pore bridging. These minerals tend to have high surface area, which result in decrease in FZI and in turn increase in reducible water saturation. Second one is fine grains, which cause increase in capillarity of pore throats, hence more water and pore permeability. So how we can apply the FZI approach to characterize hydraulic flow intervals or zones? As we mentioned earlier, FZI approach is expressed by the following equation. FZI equal reservoir quality index, which is the first part. Our reservoir quality index equal the constant value multiplied by the square root of porosity divided by of permeability divided by porosity. The second part is the normalized porosity index, which equals the effective porosity divided by 1 minus porosity index. Then both equations represent the final result, which is the FZI. Next, we will do an exercise showing the workflow of FZI technique application, and we will use core data for a single well. But before we go to exercise, this is very important reference to get for FZI to gain more information about this technique. The second one can support your knowledge and add to your experience about porosity and permeability relationship application and reservoir evaluation. Now let's go to the exercise. We'll do the exercise using Microsoft Excel. So what you see here are core data for 5 carbonate fishes described from core taken from well X. So we have Facies 1, which belongs to deep lagoon, Facies 2 belongs to reef complex, Facies 3 belong to shallow lagoon, Facies 4 shoal, and Facies 5 belong to for reef environment. This is a FK plot or porosity permeability plot for each individual facies in different colors. What you can see is that the relationship between permeability log and porosity is not perfect with the scattering pattern of the points. Also, you can see that permeability increases by several orders of magnitude against porosity unit. Such plots doesn't support reservoir quality understanding and cause confusion and distract estimation of permeability as dependent from porosity. So we can use FZI technique to reorganize the points in clusters that represent more solid correlation between porosity and permeability log, and then we will be able to characterize different rock units with unique petrophysical properties and predict permeability for each individual facies. I made a copy of this data and we will in this sheet, and we will apply FZI technique in this sheet. So let's start. What we have here, we have core data, porosity and permeability for well X. Now first let's work on the first part of FZI equation, which is RQI, reservoir quality index, which is this equation. First let's calculate K-phi ratio. So we come here in the new column, we say K-phi ratio, and we do this equation. So we divide permeability by porosity. Now to quickly apply the same equation in the other cells, we come to the corner here until the cursor change into plus mark, then we click twice and Excel will apply the equation in the other cells downward. Now we come to the second part of the equation, which is the square root for K-phi ratio. So we come to another column, we say square root for K-phi ratio equal, so we say square root and apply the other cells. Now let's calculate RQI. What RQI equal constant 0.0314 multiplied by square root of K-phi ratio, and you apply the same in the other cells. Save. Now let's come to the second part of the FZI equation, which is normalized porosity index. Come to another column, we say porosity index. So we say equal porosity divide open bracket 1 minus porosity close bracket and enter. Now finally we have the two parts of the FZI equation. Now let's calculate FZI. Equal reservoir quality index RQI divide porosity index. Now we got FZI values. What we will do now is to reorganize or sort the FZI values from minimum to maximum, or maximum to minimum. What I will do here is from smallest to largest, from minimum to maximum. So why do we do this? To generate clusters of core data, as each cluster reflects certain FZI ranges. Actually, what I will do in this exercise, I will generate 4 groups of FZI, and if I don't get a meaningful plot with unique clusters of data, I will change the ranges. So first group, we will go to insert, bring text box. So group number 1, we have FZI bigger than 0 and smaller than 1, and group 2, we have FZI bigger than 1 and smaller than 2. Group 3, we have FZI bigger than 2 and smaller than 3. And finally group 4, FZI bigger than 3. Oh, sorry. Let's plot porosity and permeability for each FZI group. So we start from we start from 0 and end. We will create a plot for porosity and permeability for FZI between 0 and 1. So we can start from here. We have 0.17 and we go down to the last point before 1. It's supposed to be less than 1, so we stop at 0.99. It's not much difference between 999 and 1, but let's be consistent with the groups that we have. So I have the points now. Let's insert a chart, points chart. This one. Now I have my plot. Okay, let's make things more organized. So I change the maximum minimum for porosity. Let's make it 0.4. Okay, and make logarithmic k in logarithmic scale, since we have oh yes, okay, and make the intersection with 0.001. Yeah, that's good. Let's call it FZI plot, and we add axis title, have porosity and permeability log. Now let's come to the second group. We plot the second group of FZI. Select data. We call this first group number 1. Now we add second group number 2. X is the porosity. We go to the last point where we stopped and start collecting the data for the second group. Okay, we have porosity and permeability. Okay, starting from 1 and move to yes, we will stop. So you will stop at 1.99. Oh, it's supposed to take porosity only. Okay. Yeah, okay. Yes, okay. Yeah. This is for porosity. Now we come to permeability. Let's see. Down. Yes, this is the second group. Let me move my plot close the top. Okay, let's come to the group number 3, which is between 2 and 3. And let's get X values, which is porosity, starting from yes. Now collect porosity between 2 and 3. Well, it's very small value. It's not so many points. Yes. We get permeability. This is group number 3. Now we come to the final one, which is FZI larger than 3. Group 4. Sorry, 4. Start from this cell. Yes. Yes. Now we have the plot for porosity and permeability for the 4 groups of FZI. You can see that we generated 4 clusters with trended change in porosity versus change in permeability, as well as change in permeability versus porosity unit by several orders of magnitude. And for this reason, I will not use linear function, but instead I will use power function to represent the relation between both. So let's come to the first group. Click and right click and add trend line. Apply power function. Display the equation and the regression value. So this is the we will use this equation to generate or to calculate permeability log from porosity. And this regression value is to quality control the correlation and confirm that the correlation is good. So as long as the value of the regression is higher than 0.6, it's perfect correlation. Let's come to the second group. The same at trend line. Power. Display equation and regression. Third group. And finally, fourth group. Now each group show perfect regression, which indicates that the porosity and permeability correlation is perfect. So, as conclusion, FZI technique enabled enable the identification of high K intervals represented by group 4, which is in purple color, where K exceeded 100 where the points exceeded 100 millidarcy, and for group 2 and group 3 and 2 the K points are falling between 10 and 100 millidarcy. So each one of these groups will almost have different production behaviors. Now what I will do, I will take these equations to my project in Petrel model and create FZI property. We will do this together in another video. Thank you for watching, and keep learning.